Okay, what is the largest rectangle that can be inscribed in a semicircle with radius r? Before we get started, let's just think about what our goal is. And this is an optimization because we're looking for the largest, which means I need to find the global max or global min. Well, clearly if it's largest, it's going to be the global or absolute maximum. I need a formula that will allow me to do that. It's going to be a two-variable equation. So let's get started. I'm going to draw a circle first. Do the best I can for a half circle. And radius r. And I'm inside of that. Let's make this a little bit larger. I'm just going to put a rectangle inside of here, and I'm not making any assumptions about how big to make it. I'm just drawing one to represent a rectangle. Now, this rectangle has a length across the top, which I will label x, and a length going up, which I will label y. What do I know about this rectangle? Okay, what I know is the area of this rectangle is its length times its width, and that's what I want to find, the largest rectangle, the biggest area. However, I've got too many variables, and I'd like to get this to less variables. So that's going to be a little tricky. How am I going to do that? Well, what I know is if I connect this straight up and down, because this is halfway through the circle, I get a 90-degree angle there, I get one box, or one half. And if I connect from the center to any point on the edge, specifically where the rectangle touches, that must be a length of r. Now, don't confuse yourself. X is not 2r because it doesn't go all the way out here. So, take a good look. X is clearly smaller than 2r's. Now, I am going to use some trigonometry here and introduce a new variable, theta. There's a reason. Y over r equals the sine of theta, or y equals r times the sine of theta. My pen's getting a little bit glitchy today. Wonderful. Okay. Now, r is a constant, which means y now is directly described in terms of theta. What about x? Well, this piece up here, r actually on r, the bottom of this rectangle is 1/2 x. And I know that 1/2 x over r equals the cosine of theta, or x equals 2r cosine of theta. Now, x is in terms of theta, y is in terms of theta, and this is important because area equals x, which is now 2r cosine of theta times y, which is r sine of theta. I only have two variables. Theta is one variable, and my area is the other variable, because r is the size of the circle, and that's fixed. We don't know its size, but it doesn't matter. It's not part of what can change. Only thing that can change is the rectangle we put inside the circle. So I'm going to clean this up just a little bit. Area equals 2r squared cosine of theta times sine of theta. Now, what we have is something I can take the derivative of. I'm going to use the product rule on these two components. The first is a constant, so when I take my derivative, dA d theta, we get 2r squared, and now I'm going to use the product rule. The derivative of the first of cosine is sine, so I get sine of theta times sine of theta plus cosine of theta times the derivative of sine of theta, and the derivative of sine of theta is negative cosine. So since it's a positive times a negative, it's going to end up being negative cosine of theta. I've got the derivative, set it equal to 0. So since this is a constant, that can't be set equal to 0. So now I know that sine squared of theta minus cosine squared of theta equals 0. Or where sine squared of theta equals cosine squared of theta. Technically plus or minus, because if I take the square root to solve for this, I end up with sine could either equal plus or minus cosine. However, we have to be concerned with what theta is allowed to be. So if we look at theta, let's go back to theta. That's my angle here. Theta can only be between 0 and up to pi over 2. The only place that sine of theta will equal cosine of theta inside of that is at exactly theta equals pi over 4. It's our 45-degree angle. So we're hoping this is going to give us the largest conceivable area. Let's find out. So let me back up here to my area formula. Oh, I didn't give the domain. Let me back that in. My domain of that angle theta. We can still find it right now. So if theta was getting smaller and smaller, x would disappear when theta gets 0. So the lowest theta can be is 0. And as theta gets bigger and bigger and bigger, when it gets to pi over 2, when it got lower and lower, x would approach 1, y would disappear. As you got closer to pi over 2, y becomes closer to the radius and x disappears. So the domain is 0 to 2 pi. Now clearly, the area at both of those is 0. So the only possible maximum I can come up with is the area at pi over 4, and I can calculate that because my area, let's go into the original formula, area equals 2r squared times cosine of theta, and cosine of pi over 4 is square root of 2 over 2 times the sine, and they have to be equal at that point, square root of 2 over 2. These reduce out, and my area, the maximum area, these reduce out, leaving me 1 on bottom. Square root of 2 times the square root of 2 is 2, and those two reduce out. my area becomes r squared. And the dimensions, I can find the size of x and y with substitution. Let's do y first. Y equals r times the sine of theta, and the sine of pi over 4 is square root of 2 over 2. So y simplifies a little bit, r square root 2 over 2, and then x equals 2r cosine of theta, and cosine is square root of 2 over 2. These twos reduce, and x equals r square root of 2. Those are the dimensions of the largest circle the largest rectangle I can inscribe in a half circle, and the area of that rectangle will be r squared.